Okay, ladies and gentlemen, thank you very much. Sorry for that, I just arrived in my room. My name is Alex, I'm Alexander Weikert. I'm the Business Director of Vexel Imaging. I would like to talk with you about UltraMap. That's our new processing software for our UltraCam digital area camera. The standard workflow is image processing, where we process the images from the raw images of the camera to the level 3 images. And what we are now adding, what we are now here announcing at the show, you can have a view and at our booth, at the Microsoft Vexel booth, is a dense matching module where we generate 3D data out of the UltraCam images. And that dense matching module allows to generate automatically from aerial images, from UltraCam images, a point cloud, a surface model, a terrain model, and then we combine the images together with this information in a so-called also pipeline module to generate the surface also, or we call as true also images, or the terrain also images. So that's an overview about a new workflow we are announcing here, where we are allowed to generate 3D data out of images. And it all starts with a set of aerial images. This is a highly overlapping, highly redundant data set of UltraCam images, typically flown in an 8060 flight. And then we do a dense matching pixel by pixel, and as a result we are getting a high resolution data set, a high resolution point cloud. And this slide shows the point cloud, what we are achieving out of such a dense matching approach by UltraMap. All the blue dots you see here is a 3-dimensional coordinate. It's a point like we are used to get it from airborne laser scanning, but here it has not been derived by airborne laser scanning, it has been derived by a dense matching of aerial images. Point density is about 300 points per square meter, so significantly denser than what you get from LiDAR. Another example, and also if you look on the right on this church tower, you also can see that very thin little objects are represented extremely well. And when we have the point cloud, we can smooth it together and generate a surface model out of it. That's a shaded relief of a surface model. And when we have the surface model, we can take the aerial images and overlay it and generate the so-called DSM also images or true also images. That's an also image which has been rectified by a surface model, and so you don't have any perspective view. Wherever you look inside the image, all the objects are completely precisely rectified and are vertical. So you don't have any leaning walls. And that's due to the underlying rectification with the surface model. Another example, the surface model of a building generated out of UltraCam images, and this is an overlay with the aerial image, and by that we get these results. And then the next step is, of course, we have the surface model, we filter the surface model into a terrain model, and then when we use this terrain model and apply the images, then we come to the classical also image. And that's a workflow we are currently demonstrating at the show, completely new additional modules. And what we expect is that we see a significant change in the industry, where we see applications served by LiDAR will go to photogrammetry. And that brings me to the end of my presentation. I would like to thank you very much for your attention. Thank you.
Mr. Su. Flashlighter.
So please swing by the booth. I'm the troublemaker today. I'm sorry. Please swing by the booth where I can show you in more detail. Thank you.
William Newton, Bundeswehr Munich.
Thank you very much. My name is William, and my work is about finding cuboid-based building models in point clouds generated from image matching. Now, the advantage of our approach in generating point 3D models, building models, is twofold. First, we like to generate a model that is going to incorporate the semantic of the building, as well as to achieve a reduced amount of data within the model, rather than generating blindly triangulated meshes with huge amount of data and almost zero semantic. Now, our approach is the first stage of our approach. We determine the vertical direction of the scene using the point clouds alone, and having got this vertical direction, we segment oriented planes using Ransack. Now, these oriented planes are going to represent building walls. Meanwhile, planes are infinite geometric entities, so we have to limit the outlines of the building walls by using a line sweeping approach, as well as plane-to-plane intersection, line of plane-to-plane intersection. This gives us then surfaces which are then consistent to our building walls. These are some few results of our algorithm gotten from data sets, self-acquired data sets, as well as data sets from benchmark databases. Presently, we are faced with a problem of varying point density from point clouds from matching, and furthermore, we are working on possibility of integrating this basic 3D model into complex building scenes with L, U, and possibly more complex building scenarios. And the next step, we shall refine these building models to incorporate other building parts like windows, doors, balconies, and further building parts. Thank you very much. And for further details about my work, I'll be down in the exhibitors hall in front of the France Paris 2016 Isprs desk. So if you want to get further details about my work, you meet me there. Thank you very much.
Mr. Wu.
Thank you, Chairman. Greetings, ladies and gentlemen. I'm John Law. The co-author is my advisor, Professor L.C. Chen. And today, it's my honor to introduce our new algorithm for point cloud processing. Our focus issues, because different buildings may need different ratios to derive better results. But when the point density increase, the computation may also increase. So this research, we just proposed a hierarchical concept to detect the structure, the approximate structure line in the green data, and include the point clouds to refine the results. And our target include two parts. The first one is the building boundaries, and the other one is the parapets on the rooftops. And within this whole process, we only use one constant threshold to detect the structure lines. Our major concept is very simple, because structure line have some geometric properties. So the locations have low relief along the direction, and may have large relief across the line direction. So we use this kind of characteristic instead of other visual operation. The whole procedure is like this. We have three parts. The first one is the pseudo-grid generation. The second part is the structure line detection, and the third one is the 3D line formation. In this, today we just propose two cases, flat roof and one flat roof with the parapets. And this is the result after we generate the pseudo-grid with 0.5 grid size. And the second part in the detection, we just use 3x3 grid to estimate two different directions to estimate the candidate age grids and compare our design patterns to derive the approximate structure lines in grid data. Then we input the original point clouds to derive the 3D structure lines. Yeah, like this in different views. And we also compare with the result of segmentation result is about 30 centimeter. And our conclusion, because right now it's just our preliminary result, and this result indicates that the proposed scheme can obtain quality of building structure lines without ratio selection, or only one constant ratio. And our ongoing work is to develop a structure-based registration procedure for aerial photos and airborne radar point clouds. Thank you.